Good afternoon, everyone, or morning or evening, whenever you're deciding to watch these videos. We are going to continuing on talking about the atmosphere. So in today's set of videos, we're going to talk about the structure of the atmosphere. So what does it look like as we go up or down? And then we're going to talk a bit about seasons and the heating of Earth's surface. Is it even? Is it uneven? What causes seasons? What happens to incoming sunlight as it travels through our atmosphere, as well as getting into atmospheric circulation. And I think that's where we're going to finish up for today. So lots of things, and it may be some things maybe a little new for some of us. So do keep that in mind, and if you get a little bit lost or a little bit, some things get a little bit funky, do be sure that, these are all recorded, and so you can rewatch them as much as you need in order to understand the concepts, as well as working through the problems on our homeworks and things of that nature. And of course, you are more than welcome to reach out for any further clarification. The atmosphere is my bread and butter, and so, some things can be a little bit funky, but that's okay. All right, so here we go. The first thing I want to talk about, especially after talking about all the components of our atmosphere and the molecules that make up our atmosphere, is the structure. So it's really, really important to recall that the Earth's atmosphere can extend about 10,000 kilometers from the surface of the Earth. But 98% of that mass is concentrated within the bottom 26 kilometers, right? So the whole atmosphere is really, really, really huge, but most of its mass and most of its bulk is down here near the surface. And the atmospheric pressure is greater at the surface. So pressure decreases nearly exponentially as you go up into the atmosphere. So it's pretty wild. It's like there's a really big extension there. And something to even keep in mind is, some of the satellite images that we look at the beginning of our in-person classes, where satellites are. And most polar orbiting satellites, are the ones that get some really good high resolution imagery, are about 800 kilometers above the surface of the Earth. So way, way, way closer than the extent of our atmosphere as a whole. So something that I want to also bring to light is how temperature behaves as we go up into the atmosphere. So I want you to think about what you think the temperature does as we go up. And would that be the same in every layer of the atmosphere, or could there be some sort of difference there? So think about it, hypothesize. And here we go. So just to kind of explain this graphic a little bit. So we have here, this is an average temperature profile of our atmosphere, with the temperature on our x-axis and altitude on our y-axis. And this orange line is the given average value of temperature. And what we also have here is the split of different layers of the atmosphere. So down here at the surface, we call this the troposphere. Then in the middle, it's called the tropopause, or in between these two layers, tropopause. Then we have the stratosphere and the stratopause, the mesosphere and the mesopause, and then finally, for our purposes, the thermosphere. We do also have the exosphere and the magnetosphere, but those are much further away from the surface that we don't really account, or we don't mess with them, or in terms of for our purposes, but those do certainly exist. So try to see, the sort of pattern that exists here. So we can see that temperature decreases in the troposphere on average, not always, but on average, temperature goes down as we go up. A way that you can remember that is like, If you look up at the coastal mountains, and you can see that, or even the Sierra Nevada mountains, when there's snow on top of those mountains, it is certainly cold enough for the snow to exist. And then down here near the surface, it tends to be warmer, where snow cannot exist. It would melt away in the form of rain. Then we can see here that there is a slight inversion or an increase in temperature as we go up, and this is in the stratosphere, right? We talked about the ozone layer in class last time. And remember that ozone absorbs UV radiation. So when it's absorbing sunlight, then it warms up that layer. And then the temperature decreases again in the mesosphere. We have the mesopause, and increases again in the thermosphere. And so this vocab word here, inversion, just means basically going upside down, right? These inversions keep the atmosphere extremely stable, and so it does not allow for any sort of mixing between the troposphere and the stratosphere. Or it takes a lot to go from one to the other. So that's why all of the weather that you've ever experienced in your whole entire life has only been down here in the small layer of the troposphere, which is kind of cool, right? There's a reason why things don't keep penetrating all the way through our atmosphere. The stratosphere keeps everything nice and down here in the troposphere. So if we were to consider pressure, which is this middle column here, and density, which is the far right column, we have to keep in mind that our atmosphere here is compressible. So that means that pressure decreases exponentially with height, and so does density, right? So the further up you go, the less air pressure there is, and the less dense the air is as well. Another way that you can think of pressure, by the way, is like how much atmosphere is on top of your head. If there's more atmosphere on top of your head, then you have higher pressure. If there's less atmosphere on top of your head, then there's lower pressure, right? So if you were to climb to the top of this little mountain here in this schematic, then you would have a less atmosphere on top of your head. Thus, higher regions like mountaintops tend to be in lower pressure regions. Now consider how the sun interacts with the surface of the earth, right? So we are a globe. Sorry, flat earthers, but we are a globe. And the sun comes down onto the surface of our planet, right? And think about if the sun reaches the surface of our planet in the same angle all over the world. So think about it. Would that happen? Is that true? And we know that that's not, right? So it turns out that the sun's energy as it comes into our atmosphere is way, way, way more spread out near the polar regions and really direct at the equator. So I like this schematic a lot here at the top. So you can think about it like a light bulb, right? So if you have a light bulb straight up and down, then you're going to have a really direct light. And then the further that you angle that light, the more spread out that resulting light on your surface is going to be, right? It's not saying that the value of the sun's energy is changing. It's all the same. Oh gosh, so sorry. Like the amount of energy doesn't change from the Earth's equator or polar regions. It's just that how much of it reaches the surface or the angle in which it reaches the surface can cause some differences, right? So what this does is creates a surplus of energy at the equator and a deficit of energy at the poles. And this, in turn, drives air circulation and energy transport as well as ocean circulation. So if we have too much at the equator and not enough at the poles, then the planet is going to try to balance itself out. And that's one of the reasons why we have these weather patterns and ocean patterns, oceanic circulation patterns that we observe. And we can see that in this image here as well. So the x-axis here is latitude with the North Pole on the left and the South Pole on the right, and the equator in the middle. And the y-axis here is calories per centimeters cubed per minute. So just a way that you can think about that is energy. So we can see that we have a surplus of energy near the equator and a deficit of energy near the polar regions, with a little bit of a sweet spot kind of in the middle latitudes, which is right about where we are located by the way. So again, the planet is always trying to maintain balance. And so we have this transfer of energy through the oceans and through the air in order to help divvy up this excess energy that exists near the equator. And a common misconception with one of the reasons that we have seasons, so it actually turns out that it's not due to how close or how far away we are from the sun. It's all about the tilt. So our planet is on a tilted plane, right? We're not straight up and down. We do indeed have a tilt. And we revolve around the sun in a more elliptical fashion, not a perfect circle. And so in the summer solstice, the North Pole is more pointed towards the sun. So there are parts of the North Pole that have 24 hours worth of sunlight, whereas the South Pole is complete darkness. And then in our winter time, the opposite is true, right? So the North Pole is then pointed away from the sun and the South Pole is pointed towards the sun, right? So it's all about the tilt. It is not about how close or how far we are from the sun. It actually turns out that in the winter time, in our winter, we are actually closer to the sun than in our summertime, by like 7 million square kilometers or something like that. It's pretty interesting, pretty wild. So it's all in the tilt, not the distance. And then this graph here is just looking at seasonal variation in solar radiation. So the green dotted lines are trying to indicate the North Pole, or the Northern Hemisphere, excuse me. The red solid lines are for the South Pole, or Southern Hemisphere. And this black line is to emulate the equator. And this is just looking at how much sunlight is coming into the region throughout the months. So the big thing to point out here is that the Northern Hemisphere sees our maximum of sunlight in the summertime and a minimum amount of sunlight in the wintertime. And then the opposite is true for the Southern Hemisphere, where there's the maximum sunlight in their winter time, in the winter months, and a minimum of sunlight in the summer months, which is kind of wild. So that's that. That's the structure of the atmosphere, as well as how the sun heats the surface of the atmosphere. So in the next video, we'll talk about what happens to incoming sunlight as it journeys through our atmosphere, and then talk about atmospheric circulation. So thank you so much for watching, and reach out if you have any questions.